Okay, example 2, you'll notice that this is exactly what we just did in example 1. It's the same function. This is the function is approximately equal to this line. Okay, that's a linearization. That's how you write out a linearization idea. So the function we linearized is approximately equal to this, but we want it accurate to within a half within 0.1. Okay, here's how we do that. This is completely done on a calculator. Bring my calculator over here. Did that on purpose, you can see that. Got to do it on a calculator. All right. 1 over the square root of 4 minus x is my original function. All right. X over 16 plus a half is my linearization. And rather than having this one, I'm going to delete this one, so I'm going to clear that out. All right. So I want my original function. What I want to graph is I want to graph an error window. Okay, and here's how this looks. That doesn't look good. Here's how you graph an error window. Here's my approximate value, right? That's the approximation. Anytime you want to create an error window on your calculator, you want to start with the approximation. And then you want to look at how much error you're allowing yourself. Specifically, 0.1 and 0.5. Those are my errors. Okay. Error, as I've said many times in this class, error is not meaning that you're wrong. It's meaning how far you are away from the accepted answer. All right? If you have a huge answer and you're off by 0.1, not a big deal. If you have a really, really tiny answer, you're off by 0.1, that could be a really big deal. Error has to do with not just how far you're off, but how big the number is to begin with. So if the answer is 15 trillion, you're off by 0.1, nobody will notice. If the answer is 0.1 and you're off by 0.1, that's pretty noticeable. Right? You're supposed to have a dime and you have 2 dimes, yeah, that's pretty noticeable. You have $15 trillion worth of dimes and an extra dimes in there, I can't tell. Okay, kind of think of it that way. All right, so what we're looking at here is an error of 0.5. That means 0.5 too much, 0.5 too little. Okay, so here's what it looks like. 1/2 plus 1/16 x plus 0.5 and 1/2 plus 1/16 x minus 0.5. How much is 0.5 in fraction world? 1/2, right? So this one here, if we're adding a half to a half, we get 1. So we get 1 plus 1/16 x. And we get 1/2 minus 1/2 is 0, right? 0 plus 1/16 x. All right. So I want to graph these two. This creates my error window. All right. So let's do that. So 1 plus 1/16 x. 1/16 x is easier to type in as x over 16. Forgive me that. And the other one's just 1/16 x, so x over 16. All right? And if I change my window now, we've got really zoomed in before, I'm going to make it go from 0 to 2 here. Well, actually, let's go from -1 to 2. All right? And let's go from -2 to 2 on the x also, because we're not sure yet. -2 to 2. Uh-oh. All right, hit graph. Okay, the blue curve is my exact answer, right? The right answer. The red curve is too much, the black curve is too little. I want my answer to be within a half of the right answer. Okay, so that's the window I'm allowing myself to be in order to get an answer. All right? What I'm looking for is for my blue curve to intersect one of these. Because once it intersects, then I'm outside that error range, right? So there's where I'm at. I'm allowing myself a 0.5 error on this problem, so I'm allowed to get this far up, this far down, and the right answer is the blue line. Once the blue line crosses one of these two lines, now I'm outside that error window. Does that make sense? So the red line and the black line is my error window. I want to stay in between that, and right now the blue line's in between that. So currently, I'm in good shape. As long as I'm within, this is 2 and -2, right? So if I'm 2 away, I'm still within a half. We're good. So I got to go further out. So I'm going to go from -10 up to 4. The reason I'm stopping at 4 is because, again, I know I can't put a number bigger than 4 in. All right, so I'll hit graph again, see what happens. Okay, there's my blue curve. And there's my red curve. Notice the blue curve got outside the error window right here, right? It's still within the error window there. The black curve doesn't even matter. Why doesn't the black curve matter?
Because it's not touching the blue one.
Right, and the blue line is staying above it because we had an underestimate, right? So the overestimate is the thing that's going to be intersecting more than likely. All right. I didn't go far enough back here, so let me go a little further back. Let's go back to -15 maybe. There's no scientific way to do this. I'm just playing around with numbers till I see a cross. So still going to cross over here, obviously. Oh, look, it crossed over there too. Excellent. So right here and right there, those two values represent the places where the curve itself, the blue curve, is within the error window. 1/2 too big, 1/2 too little, blue is in between, too big and too little. It stops here and there, and again the black line has no bearing on this. I personally do the top and bottom every single time, so I don't even worry about the underestimate and overestimate that much. Okay? If you get an underestimate, the one you add is going to be the one that matters. If you get an overestimate, the one that you subtract matters. If you make an error window every time, it's not that big a deal to type a third function in. So I always put the top and bottom in. I look at this picture like this. And what I want to find is this point and that point. Those are the x values. All right, so how do I do that? Calc intersect. We're trying to find a point of intersection, okay? Now, usually when we do calc intersect, we have one point of intersection and two curves. Now we have three curves and 2 points of intersection, so we have to be a little more exact about what we're doing. So if I go to my second calc 5, the things it's asking me for is first curve, second curve, and guess, okay? So, which curves do I want? The blue and the red. Okay, right now it's blinking on the blue, which is good. If you didn't know that, it says at the top, y1 equals, but it's blinking on the blue. The way you switch between curves, you push up or down, jumps to black, jumps to red, jumps to blue. Okay? So if you don't know what curve you're on, and plus it's in blue, now it's in black, now it's in red. So with these TI-83 plus calculators, silver edition, or TI-84 plus silver edition even, all right, 84 instead of 83, anyway. It has colors on it. So it shows you what's colored. So the curves I want are the blue and the red, so I'm on blue. It doesn't matter where you're at. You're picking your curve right now. Hit enter. Now it jumps to red, which is exactly what I want. Hit enter. Now the guess is what matters. Okay, right now if I guess just that, it's going to jump to one of them or the other one. I don't know which one. I can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Around -12, right? If I type in -12, it's going to find me the answer near -12. Exactly, -12.25. Excellent. So, -12 is the low end. All right, and then if I pick this one up here, same deal, go to calc, intersect, calc 5. Again, it's going to say first curve, second curve. Right now it's blinking on the point we just went to, right? But again, I know it's on the blue curve. Now I know it's on the red curve, just based on the colors. As far as the guess here, that looks to be around 3, so I'm going to type in 3. And it's 3.3137085, comma 1.20710068. So x equals 3.3137085. Now I know that I want my answer to be in between those values, right? So x equals -12 is a point at which they're exactly the same. This one here is more approximated, right? Okay, round down, don't round up. They want a window of error reliability here, a window of tolerance. Chop off more than you add to it. So what I'm saying here is if I went to, let's say 3 decimal places, 3.314 is what you'd round up to, but 3.314 is an error of more than 0.5 because it's to the right of that, okay? So round down. So if it said to the nearest thousand, let's say 3.313, go with that. That'd be more accurate than 3.314 because again, you want it between these numbers. If you go 3.314, you want outside that window. Does that make sense? Everybody? So I'd say for the point to within 0.5, I would go -12 up to 3.313. And I could actually put a bracket around the 3.313 even. Okay. Because again, I rounded down, that guarantees me that 3.313 is fine. If I round it up, 3.314 isn't. And if I put a parentheses at 3.314, then I'm allowing 3.3139, which is outside the window. So again, you want to put a bracket there. You want to stay within the window, round down every time. All right? To do the 0.1, it's the same idea, just different numbers happening here. So let me just do this. Shrink. All right. So thinking about this, if we want the accuracy to be within 0.1, that's more accurate, right? Should the window be bigger or smaller? Smaller. Smaller, right? 0.1 error instead of 0.5. So 0.5 error, we're allowed to be 0.5 away. Now it's 0.1 error. That's shrinking that window. If that window shrinks, imagine shrinking these down, we imagine that the points should be closer together, right? The error tolerance is less, so the window of opportunity is smaller. Okay, so that's a 15.313 wide window there of opportunity. So as long as we're within those numbers, that linearization is within a 0.5 value. So if we go to 1/10, so 1/2 plus 1/16 x plus a tenth. That's 5/10, that's 1/10, so it's 1/16 x plus 6/10. 6/10, same as 3/5. And if I do subtract a half, or subtract a tenth, so 1/2 plus 1/16 x minus a tenth, again that's 5/10 minus 1/10 is 4/10, so that'd be plus 2/5. All right? So again, I want to know what y2 and y3 should be. y2 simply add the error you're allowing, y3 subtract the error you're allowing, and then simplify as much as you possibly can. So y2 equals 1/16x plus 3/5 plus 3/5, 1/16x plus 2/5. And again, this is going to be above the curve, this is going to be below the curve, and again, I'm looking for that window of opportunity, and I know it's going to be smaller, so it should, if I keep the same window, it should be in there. Might not be as easily seen, but we'll find out. Red line intersects there, intersects again there, so there you go. There's the black line below it, never ever touches it. All right? So again, we're looking for points of intersection, the blue and the red. And again, I can see very clearly that there's points of intersection. That's fine. If you want to get a closer zoomed in value, -5 to 3 looks like a safe window here. So window, I go from -5 to 3, and let's go for y min 0 to y max, let's say 1.5. I think everything stayed within that. Let's see. There's my blue curve. Is exactly right. Red curve is too big. The black curve is too small, and we can just get a better, closer view of that. So this looks to be close to -4. This looks to be close to +2. So when I do my calc intersect, again, the lines intersect to the blue and the red. So I hit blue, enter, red, enter, guess -4, and we get -3.911647. And the other point of intersection, first curve blue, second curve red, guess 2. We get 2.1438131. Again, if I go 3 decimal places again, rounding down, I'm going from -3.911 up to 2.143. As long as I'm within that window, every one of my linearization values should be within 0.1 of the actual correct answer. Okay, you're guaranteeing yourself an error tolerance there. So a lot of times the error tolerance is 0.01, 0.001, 0.001 like that. If they get to be that type of thing, here's what I do. So our original function was x/16 plus a half, right? All right, plus 0.001. Okay? That works. And then if I do x/16 plus a half minus 0.001, and that's going to be a really small tolerance there. So I'm going to set my window really tiny here. So I'm going to go from -1 to 1, and from .5, I'm sorry, 0.45 to 0.55. If you don't zoom in a lot, you won't see these. There's the answer, the exact answer. There's my overestimate. And there's my underestimate. And it's really, really, really tiny there, right? So you can't even see that. So I might even, if this is -1 to 1, I might need to go from negative maybe 0.2 to 0.2. And get in a lot closer, like maybe 0.49 up to 0.51 to get a closer look at this. Looks pretty close to being the same. It's actually outside the window there. So I went too close in, right?
Mm-hmm.
So for one thing, it went off the screen here, so I made my y's too small. I might need to make my x's a little bigger. So maybe negative 0.3 to 0.3. Let's go from 0.48 to 0.52. Again, there's no like magical way to find these. It's just you graph until you see them. You're looking for points of intersection. And now there's a little bit of gap there. Looks like intersections happen there. All right? So, situation like that, you might even just find one at a time. So if you just figure out this one here, and maybe zoom in just to that area there, and then zoom into this area over here to find them, that might help too. All right, but again, they usually look for really tiny tolerances like that. I want you to be off by just this little tiny amount, so that gives you a very small window of opportunity. All right?